Hello, this is Jack Jackson. In this video, we're going to be using the program Geometry Sketchpad and a sketch that I've created there to help illustrate the idea of what's going on with Newton's method, sometimes called the Newton-Raphson method. Now, what happens in Newton's method is we're going to try to approximate the x-intercepts of a graph of a function, or sometimes these are called the zeros of the function. So here we have a function graphed. In this sketch I can click on this and change the function if I want. But right now I have the function f of x equals 2 minus x squared, and you see it graphed. Actually it touches the x-axis a couple of times, once over here and once in here. And we're going to be interested, let's say, in finding this point right here. Now we know exactly what it is. It's 0 equals 2 minus x squared. That says x squared equals 2. So x equals either the square root of 2, which is this guy here, or the opposite of the square root of 2, which is this one over here. Now, of course, that's the only way you could say that, because, say it exactly at least, because that is an irrational number. It has no decimal expansion that terminates or repeats. However, we can approximate that to any degree of accuracy we want using, say, Newton's method. And here's how it works. We start by guessing something. Okay, now I'm going to make a pretty bad guess here to start with, but the sketch allows me to enter a value right in this box right here for my guess. And I'm going to start with 0.8, and you can see 0.8 graphed on the 0.8 comma 0, I guess, graphed on the x-axis there. Now what you do there is you go up and find the y value that goes with that 0.8. So we go up and find this point x sub 0, f of x sub 0, on the graph. So x sub 0 is our initial guess, and the y that goes with it then is f of x sub 0. And our particular point, 0.8 is the x value, and 1.36 is the y value. We could do, I mean, this function involves nothing more than squaring and subtracting. We could do this by hand, even without a calculator if we wanted to. Okay, next what we do, and here's where the calculus comes in. We want to draw in the tangent line. Okay. Now to do that, we need to find the slope of the tangent line, which requires us to find the derivative function. So this is a pretty easy derivative to compute using our shortcut rules. The derivative of f with respect to x, f prime of x, is negative 2x. Actually a very simple formula. Now what we do is we use that to get us the equation of that tangent line. Now first of all, we take f prime at x sub 0 is going to be the slope of that, in this case I have a tangent line. Okay, so that is negative 2 times the 0.8, that's negative 1.6. Okay, then the equation of a line in general is the point slope form is y equals the slope times x minus the x-coordinate of the point that we're centering at, in parentheses, plus the y-coordinate of the point. Well, for a tangent line, remember, of course that's y equals, the slope is f prime at x sub 0. Then we have parentheses x minus, then the x-coordinate of that point there, where the point of tangency that's on both the tangent line and the curve is x sub 0. And the y-coordinate of that point there is f of x sub 0, or in our case, for this specific example, it's y equals negative 1.6 times parentheses x minus 0.8, close parentheses, plus 1.36. Now we graph that, and we have the tangent line. Okay, so now what we do is we actually take this, and we want to find the x-coordinate where that touches the x-axis, where that tangent line hits the x-axis. Now this is just a linear equation, so we can solve this pretty simply. But I want to do it with the variables in place to show you something interesting that goes on here. So I take this formula here in general, y equals f prime of x sub 0 times x minus x sub 0 plus f of x sub 0, parentheses around the x minus x 0. And I want to let that be points on that line, x, y coordinates on that line satisfy that equation. And the one specifically we're looking for is the one with the y-coordinate of 0, and the x-coordinate we'll call x sub 1. So when I put in x sub 1 in place of x in that formula, I put in 0 in place of y. Now what we want to do is solve for x1. So first thing I'm going to do is subtract f of x sub 0 from both sides, and then I also switch both sides here. So now we have f prime of x sub 0 times parentheses x minus x1 close. Let me say it again. F prime of x sub 0 times parentheses x1 minus x sub 0 close parentheses equals the opposite of f of x sub 0. Now we divide by the derivative here to get x minus x1 minus x sub 0 on the side by itself equals the opposite of f of x sub 0 over f prime at x sub 0. That's pretty cool. Now we just add x sub 0 to both sides, and now we have x1 by itself. So in our particular, so we have a formula here to how to get x1 if we know x sub 0 and the formula for the function and the formula for the derivative. So in our particular case, to get x1, the x coordinate of this coordinate right here, we take x of 0, which is 0.8. We say subtract the f of x of 0, which is the y coordinate of this point up here, minus the derivative, which is the slope of that tangent line there. And we work all that out, we get 1.65, which is the coordinate of that x1. Now we're going to repeat the process again. We're going to take this point, come down, find its y, take a tangent line, find where that tangent line touches the x-axis. That'll give us x2. And then we repeat again and again and again and again as many times as we need to get the accuracy we need. And so what generally happens here is this gets closer and closer and closer to the point that we're looking at, and it does it actually pretty quickly. You'll see with one more step we're going to get pretty close. Now notice this formula that we have here basically tells us how to find x1 in terms of x sub 0. Well, this basically tells us how to find any guess given the previous one. So if you want to find the n plus 1 approximation, x of n plus 1, what you do is you take the previous x, xn, minus f of xn over f prime of xn. Or in other words, if you have any guess xn, we take xn minus f of xn over f prime of xn will generate the next x of n plus 1. So here are some values worked out, and this will also show us some of the steps again. Okay, so look here what we have. We have our first guess is 0.8. We find f of that, which is 1.36, which is this y value of this point right there, where it touches the x-axis, touches the curve. Then we find the derivative at that point, which is going to be the slope of the tangent line. We graph the tangent line and solve for where it crosses the x-axis using that red formula I had down here. So the numbers are 0.8 minus 1.36 over negative 1.6, which is 1.65. That's x1. Now that's the output of that first stage, which becomes the input for the next stage. And so now what do? We find, let's actually show the picture. So now we take this new x value, x1, go down here, straight down the curve, straight down vertically till we hit the curve, and find that y value, which is x1 comma f of x1. So that x1, remember, is 1.43106. I'm sorry, it's 1.65. Okay, and then we take the y value that goes with that, which is negative 0.72250, which is right here. So whatever that y value is, we find the derivative at that x value, which is just negative 2 times that x value, which is negative 3.3. And then we use this basic formula to find x2. We take x1 minus f of x1 divided by f prime at x1, and that works out to be 1.43106. That becomes the input for the next stage. Then we repeat the process again. Let me hide the first one. And so now you can just see the second step. Now we go from the second step, we repeat the process and do the third step there. Okay, so to find the third one, we take the y value, x value here of 1.3106, go down here and find its corresponding y, which is there on the curve, and that turns out to be negative 0.04793. Find the slope of the tangent line there, which is negative 2.86212. Okay, and then what do we do now? We find x3. How do we find that? We take x2, the 1.43, whatever, minus the y value divided by the derivative, and that gives us x3. Repeat the process here. I don't have it illustrated, but it'd be hard to tell apart from this one by just looking at it. And we get an even closer value, very little change there. And in fact, the fourth time we did it, to find x5, it's the same as x4. So we actually started with x of 0, then we had a second estimate, our first estimate from after our original guess, which is x1. Then we found x2 and x3, and there wasn't really any change. Or then we found x4, and there was no change from x4 to x5 up to this many digits. So at least with looks like 6 significant digits on this particular one, we were able to reach after 4 iterations. And so that's pretty common for this to happen, that it actually converges very quickly to the value that we want to have here. And so this iterative process is what's called Newton's method. And since it is a nice little iterative process, we can actually, without graphing it all together, we can actually come up with this as a very numerical type of procedure. And repetitive numerical procedures like this are something that are very easily programmed into, say, a graphing calculator or a computer. And in fact, it is a method such as this that the calculator uses when you tell it to calculate a 0 on the calculator.